Hi and welcome. Today I'm going to show you how you can calibrate a temperature-dependent Ansys Hyperelastic material model to experimental data. So here in my example, I have experimental data at 3 different temperatures for an unfilled silicone rubber. And I want to calibrate a temperature-dependent hyperelastic model to this data. And the easiest way to do this is to calibrate first a material model for each temperature. So to do that, I'm going to save this file into a new name. And I was going to call it T20. I'm going to start with the lowest temperature. I turn off the other 2 temperatures. But before I calibrate it, I want to add another load case for the Poisson's ratio, just to make sure we can find a reasonable value for the Poisson's ratio in this case. And I'm picking 0.495 here. We didn't have data, and that's the one I will use for this case. And I'm going to select a material model. I'm going to scroll down to Ansys Hyperelastic. And since the stress strain predictions were so simple, almost linear, I'm going to use the Aruda-Boyce hyperelastic model. So here it is. If I run it once, here is the initial prediction. I'm going to now try to calibrate this model for us. I'm going to click Calibrate, Extensive Automatic, just use the default settings, and run the calibration. And here it's done. The calibration looks good. I'm going to export this result to an Ansys APDL file. I'm just going to call it T20. There it is. And then to calibrate the second temperature, I'm going to use the same file. And I'm just going to save it in a new name. Here. I'm going to call it T60. And I turn on the 60-degree load case. I turn off the 20. And here it is. And the key is I'm starting the second calibration from the end point of the first calibration. So that gives me parameters that are in good order and easy to work with. So I'm just going to run this calibration now. Done. I'm going to now export this one again to an Ansys APDL file. Let's call it T60. That. And finally, the third case here, I'm going to save it as a, let's take a look, T150. And I'll turn on the 150-degree C test case. And I see this is the initial guess. I'm going to run the calibration from this point. And that has also finished now. So I'm going to export this one to a file, T150.dat. Those are my files. And the second step, after we calibrated it to each temperature, is to combine these files into one temperature-dependent hyperelastic model. So I'm going to take this first one. I'm going to make a copy of it. I'm just going to call it all temperatures. I'm going to open that file with the text editor. Here it is. I can get rid of some of the comments initially. We don't need those here. In order to specify the temperature, we need to add one more command here, and that is tbtemp. And then I just write the temperature, which is 20 degrees C. And I'm going to save this. I'm going to now open the second file, which was at 60 degrees C. I'm going to copy these 3 commands here, which is the parameters that we searched for. I'm going to paste them in. I'm going to copy this tbtemp command. I'm going to change it to 60. So we reproduce it for each temperature of interest. So tbtemp 150 is the last one. I'm going to have to open that file here. So these 3 lines, I paste them in. And we're done. Here's our temperature-dependent Ansys hyperelastic material model. We can use this in our Ansys simulations in any way we want. To show you how it works, I'm going to take these commands and I paste them back into MCalibration. So I select them, I copy them to clipboard. I'm switching back to my MCalibration window. And here, what I will do is I will click Set Material Model. And I'm going to go to Ansys template. I'm going to paste in these guys. I paste in these commands right here. And if I wanted to, I could make these numbers here variables. But I don't have to for my demonstration. I'm going to keep them the way they are. I say OK. Nothing shows up in the table because I didn't create any variables, but that's OK. We have a well-defined material model at this point. Then I'm going to turn on these 3 temperatures. I'm going to remove any old predictions. These are the experimental data. Before I run this, I need to also modify these load cases. I need to specify the temperature. We didn't care about that before, but we need to care about that now. So this is not in Kelvin. I didn't using the temperature unit here. The temperature is 150, and this one is going to be 60, and this one is 20. So MCalibration knows what the temperatures are, and then I'm starting to run this calculation to see if our final temperature-dependent hyperelastic model indeed works as it should. And here it is. We'll see that the predictions are very good compared to experimental data, and it works for the whole range of temperature, just like we wanted it to. So that's it. That's how you can calibrate a temperature-dependent hyperelastic model using MCalibration. You calibrate each temperature first, you combine them into a master model, and then you can use it in your simulations.